Have you ever wondered what the center of Earth looks like? What would the center of other planets look like? Today we're going to explore this hidden realm in this video. The planetary core consists of the innermost layers of a planet. They can be entirely solid or entirely liquid, or maybe a mixture of both solid and liquid layers, as in the Earth's case. The size of different cores in our solar system varies. They can be about 20 to 85% of a planet's radius. Gas giants are also believed to have cores, though having cores much smaller than those of terrestrial planets, but some have a core larger than Earth. Jupiter has one 10 to 30 times heavier than Earth. All terrestrial planetary bodies, Earth, Venus, Mars, Mercury, and the Moon, have similar inner structures and consist essentially of iron cores and silicate shells. Based on geological and petrological data available, they evolved during a similar scenario, as evidenced by existing of crucial turning point at the mid-stages of evolution of their tectonomagmatic processes, associated with the involvement of new geochemical-enriched material in geodynamic processes. However, according to paleomagnetic data, the magnetic field on Earth existed about 3.45 billion years. Because a new substance began to take part in tectonomagmatic processes much later, it is considered that liquid iron, responsible for the magnetic field in Paleoarchean, was derived from chondrite material of the primary mantle. This iron, in the form of a heavy eutectic, iron plus iron sulfide liquid, flowed down and accumulated on the surface of the still solid primordial core, generating a magnetic field, but did not participate in the geodynamic processes. Only melting of the primordial iron core, which occurred already in the middle of Paleoproterozoic, led to a dramatic change in the development of our planet. Very likely other terrestrial planetary bodies, the Moon, Venus, and Mars, were developed following the same scenario. The situation on Mercury is unclear yet. Before we talk about the cores of planets of our solar system, don't forget to like and subscribe and press the bell icon to stay tuned for more interesting science videos. So let's take a closer look at each of them one by one. Mercury. Mercury's outer core is composed of liquid metal, and now scientists have found that Mercury's inner core is solid and nearly the same size of Earth's inner core. Its core nearly fills 85% of the volume of the planet. This large core is huge compared to the other planets in our solar system. It has a solid silicate crust and mantle overlying a solid iron outer core layer, followed by a deeper liquid core and a possible solid inner core. Due to the molten core that is powering the weak magnetic field of the planet, its interior is still active. It has an observed magnetic field. Only 1% as strong as Earth's and resembles Earth's field in being roughly dipolar and oriented along its axis of rotation. Researchers believe its field is produced in much the same way as Earth's field by magneto-hydrodynamic dynamo mechanism. Venus. Venus is much like Earth in its size and density, as they are both made up of similar components. It probably has a metallic core and a mantle made up of dense rock and a crust of less dense rock. Its core is primarily composed of iron and nickel, in a similar way like Earth, but its lower density also indicates that it has somewhat other elements like sulfur. No intrinsic magnetic field has been detected for Venus though, and so there is no direct evidence of a metallic core like Earth. Calculations of Venus's internal structure suggest that the periphery of the core lies a little more than 3,000 kilometers, 1,860 miles, from the center of the planet. Above the crust lies Venus's mantle, which makes up most of its volume. Despite the high surface temperatures within the mantle are likely similar to those in Earth's mantle. Similar to heat production within Earth, heat within Venus is thought to be generated by the decay of natural radioactive materials and transported to the surface by convection. Earth. More than 90% of Earth's mass is composed of silicon, oxygen, iron, and magnesium, elements that form the crystalline elements known as silicates. The crust accounts for only 0.4% of the Earth's mass and 0.1% of the total iron present. The rest, 80 to 85% of the iron, is contained in the Earth's core. The upper mantle generates most of the basaltic magmas at a depth of 100 kilometers. The upper mantle, which is rich in the olivine, pyroxene, and silicate perovskite minerals, shows significant lateral differences in composition. The lower mantle, at present at a depth of about 650 kilometers to 2,900 kilometers, mainly composed of iron and magnesium-bearing silicates. The mantle is not static, but churns in convective motions. The Earth's core is about the size of 3,600 kilometers, nearly the size of the planet Mars, accounting for about 1/3 of the Earth's mass. It is mainly made up of liquid iron alloyed with nickel and other lighter elements. We are sure about its liquid nature because of shear-type seismic waves which are unable to penetrate the core. A small central part of the core at a depth of 5,100 kilometers is solid iron. The inner core is divided in 2 layers. This is known by the polarity difference of iron within them. Iron crystals in the innermost layer are oriented in east-west direction, and the orientation of the outermost layer is north and south direction. Temperatures are extreme, ranging from 4,000 Kelvin to 5,000 Kelvin at the outer core, and about 5,000 to 7,000 Kelvin in the inner core. About 1/5 of the heat that flows to the surface is from the core's reservoir. Helical fluid motions in Earth's electrically conducting liquid outer core have an electromagnetic dynamo effect, giving rise to the geomagnetic field. The planet's sizable hot core, along with its rapid spin, probably accounts for the exceptional strength of the magnetic field of Earth compared with those of the other terrestrial planets. Mars. Not much is known about the interior of Mars. Its central core has a radius of about 1,200 kilometers, collected from isotope 2,000 kilometers, as indicated by its moment of inertia. Data collected from isotopic meteorites that the planet separated into a metal-rich core and a rocky mantle 4.5 billion years ago. It possibly contained core-generated magnetic field in the past, which might have stopped within 0.5 billion years of its formation. Its core might be more sulfur-rich and the mantle might be more iron-rich, as suggested by the meteorites. Mars is almost certainly volcanically active today, although at a very low level. Some Martian meteorites, which are all volcanic rocks, show ages as young as a few 100 million years, and some volcanic surfaces on the planet are so sparsely cratered that they must be only tens of millions of years old. Jupiter. The atmosphere of Jupiter only makes up a small fraction of the entire planet. No direct observations of the Jupiter's core has been made, and it's hard to draw conclusions. But from observed quantities like temperature, pressure, mass, shape, radius, rate of rotation, etc., theoretical descriptions and models have been proposed. The center temperature is estimated to be around 25,000 Kelvin, consisted with the internal source of heat inside Jupiter, which allows it to radiate twice as much energy as it receives from the Sun. The pressure at the center ranges from 60 to 100 million atmospheres. Under such enormous pressure, it is believed that hydrogen might be present in metallic state. It is made up of about 70% hydrogen and 24% helium. Astronomers have concluded that some helium that was dissolved in the fluid hydrogen in the planet's interior has precipitated out of solution and sunk towards the planet's center, leaving the atmosphere depleted of this gas. The precipitation is constant as the planet is gradually cooling down. It is evident from the recent models that transition from molecular to metallic hydrogen occurs at 1/4 of the distance down towards Jupiter's center. No solid surface exists in any of these models. Most models include a dense core with a radius of 0.03 to 0.1, that of Jupiter. Although there is not much information about the source of internal heat, the most favored explanation involves a combination of the gradual release of primordial heat left from the planet's formation and the liberation of thermal energy from the precipitation of droplets of helium in the planet's deep interior. It has one of the most strongest observed magnetic field in the solar system generated in its core. Saturn has a low mean density, which it provides an evidence that most of its composition is mainly hydrogen. Under the extreme pressure above 1 kilobar and extreme conditions, hydrogen is usually present as a liquid. More information is obtained about the interior structure of Saturn from studying its gravitational field, which is not spherically symmetrical. The fluid molecular hydrogen, which is present at a distance about halfway between Saturn's cloud tops and its center, undergoes a major phase transition to a fluid metallic state at roughly 2 megabits and temperature of about 2000 Kelvin. This fluid metallic state resembles a molten alkali metal such as lithium. A rock and ice mixture that is of about 15 to 18 Earth-like masses is believed to present at the central core. Saturn's metallic field is essentially produced in the same way as that of Earth's. A very striking change was observed in the last 25 years. The magnetic field lines of Saturn are made more symmetrical to the rotational axis before they reach the surface by their passing through a non-convecting, electrically conducing region that is rotating with respect to the field lines. This led to a conclusion that this might be related to the action of deep electric currents involving the conducting core. Saturn's core could have originated with 10 to 20 H-like masses built up from the accretion of ice-rich planetesimals, as suggested by the calculation made from thermal evolution. A large amount of gaseous hydrogen and helium from the original solar nebula would have accumulated by gravitational collapse. It is thought that Jupiter underwent a similar process of origin, but that it captured an even greater amount of gas. Uranus has a higher proportion of elements heavier than hydrogen and helium. It has a density lower than Jupiter. Different ratios of silicates and metals, water, methane, ammonia, and gases are proposed by different models. Uranus is shown as a fluid planet with gaseous higher atmosphere. The pressure at the center is about 5 megabars. Scientists have obtained more information about the interior by comparing a given model's response to centrifugal forces, which arise from the planet's rotation, with the response of the actual planet measured by Voyager 2. This response is expressed in the terms of the planet's oblateness. By measuring the degree of flattening at the poles and relating it to the speed of rotation, scientists can infer the density distribution inside the planet. For two planets with the same mass and bulk density, the planet with more of its mass concentrated close to the center would be less flattened by rotation. Before the Voyager mission, it was difficult to choose between models in which the three components, rock, ice, and gas, were separated into distinct layers, and those in which the ice and gas were well mixed. From the combination of large oblateness and comparatively low rotation for Uranus, measured by Voyager, it appears that the ice and gas are well mixed and a rocky core is small or non-existent. Neptune has a mean density less than 30% of Earth's and is the densest amongst the gas giants. A larger percentage of Neptune's interior is made up of molten rock materials and melted ice. Data from the Voyager 2 suggests that Neptune is unlikely to have a distinct inner core of molten rocky materials surrounded by an outer core of melted ices of methane, ammonia, and water. Heavier Xamson compounds might be spread uniformly throughout the interior, rather than being condensed at the center. The large fraction of Neptune's total heat budget derived from the planet's interior may not necessarily imply that Neptune is hotter at its center than Uranus. Though not much is known about the Jovian planets, we have tried our best to provide you with valuable information about them. What do you think about these extreme centers? Can we know more about these beautiful planets? Let us know what you think in the comments section. Also, like and subscribe to the channel, and stay tuned for more interesting videos.